I think we can go through my talk fairly quickly because when I put it together, I was thinking of large farmers. How many people have at least a 10-inch well? How many have smaller ones? Sorry, I prepared for the wrong audience. But, so you're going to get a lot about engine selection, and you can kind of tune that out. I did work for the university for a number of years as agricultural engineering department, and during the late 70s to about 1990, we had a well testing program. And we tested about 800 to 1,000 wells during that period throughout the state. I looked back and tried to find a few tests in Mesilla Valley, and there weren't any, or there were very few. Because in those days we had a full water supply. The farmers had turned off their pumps, they turned off the gas, and they weren't going to turn it on for some dumb college professor to come test the well. The few that we did test, the engines looked pretty good. The well efficiencies, as Dr. Samani said, weren't very good. And the farmers weren't concerned because they were only lifting the water about 10 feet. Gas was cheap. They got the quantity of water they needed, and so they didn't worry about it. But last year that began to change and people became a little interested. Now, first thing we have to think about when we're selecting a pump, selecting a power source here, is what's available to us as power sources. Spark ignition engines are the most common in the area, fueled by either LP or natural gas. There's electric motors for the larger farmers, 3-phase electric motor shafts. For you smaller farmers, they're single phase. Now, 3-phase is not available throughout the valley. It's not going to become available because El Paso is not looking for electrical load during the summers. They're already peaked out on air conditioning. For photovoltaics, I showed my age here by saying DC. The new photovoltaic systems have microinverters on the back. So when you put in the PV system, you can get AC out of it. And you can get AC 2-phase about 240 degrees, 240 volts. So it's already set up to run a submersible pump. And for systems up to about 10 kilowatts, the El Paso Electric has to hook you up. They have to give you net metering, and they have to pay you about 10 cents a kilowatt hour that you generate, whether you use it or they use it. If you're going to have a photovoltaic system, you have to be tied to the electric company, or else you can only pump when the sun shines. Tied to the electric company, you can pump anytime, and when you're not wanting to pump, the photovoltaic can still work and produce current back onto the electric company lines, up to 10 kilowatts. Bigger than that, you can't do it. The last one I mentioned up here is diesel engines, and there's use of diesel fuel, possible to do some dual fueling maybe with that. Spark ignition engines, advantages are it burns natural gas, the cheapest fuel. It's relatively easy to service, change the sparks and plugs, and everybody knows how to do that. Also gives you a variable flow rate. If your pump wears and the quantity falls, you just hit the throttle another notch. May not be efficient, but it's getting you the pump, getting you the water without having to change out the pump. The disadvantage of it wears with time. An internal combustion engine will last about so many million revolutions. So the faster you run it, the shorter life it's going to have. We'll talk about that later. In rural areas, we've got enough people living out there, noise is a problem, and it requires constant service, that is with changing oil and all sorts of things that you don't have to do with an electric motor. Large electric units are easy to operate, very low maintenance, long life. They possibly can be dual fueled with IC engines. You can install a gearhead between the discharge head and the motor, so you can run it with natural gas. We don't have any yet. Disadvantages, you have to live near 3-phase lines, and even if you live near, it still may be expensive to bring those lines to your house. Speed of operation is single, and if you want to irrigate your neighbor's garden, well, you just have to waste some of the water, whereas with an engine you could just slow it down. But they can be damaged by lightning. Diesel engines are more efficient than spark ignition engines. probably have longer life, and they may be able to dual fuel. We did an experiment in the last days of the old energy shortage of dual fueling an engine with natural gas and diesel. You have to have a special carburetor to do that because you can't have a throttle valve in there. So we did it thinking we could use 70 to 80% natural gas and a pilot charge of diesel. It didn't work. We could run it, and the amazing thing is when you put that natural gas in there, all the clinking and clanking and knocking of a diesel in smooths out, and it's just like a natural gas engine. But at higher rates than 50%, we didn't get very good production, very good efficiency, and so if you're going to do that, make sure somebody does it that knows what they're doing. So we didn't have a lot of luck. Disadvantages are heavier and more expensive than spark ignition engines, and there is a fire hazard and perhaps a theft hazard on the fuels that are stored out on the site. Cost of fuels is going to be our most important factor. We'll have to do that by using the energy content of the fuel, and for natural gas, the textbook values 1045 BTUs per 1,000 cubic foot. So we have to, and we buy it, so we have to multiply, this is per 1,000 cubic foot, and then we have to, the effective energy is, we have to decrease it for pressure. They say our atmospheric pressure is 13, I use 12.6 over 17. Our engine's going to be 20% efficient, so out of this BTU, out of the heat content of the gas, we're going to get about 179 useful BTUs. When you do the same thing with LP, 97,000 is your average of combination of butane and propane, divided by times the same 20% efficiency, 19 gallons. It takes 9.4 gallons of butane to equal an MCF of natural gas. So butane is about 3 times as expensive as natural gas on the same installation. Diesel fuel, 137,000 for 41,000 BTUs per gallon. A little more efficient than a spark ignition engine. Use 4.53 gallons. Our diesel fuel is about twice as expensive as natural gas. On fuel, for electricity, a kilowatt is worth about 3,415 BTUs. The electric motor is going to be virtually 90% efficient, so we'll get 3,074 BTUs per kilowatt, or it takes 58.2 kilowatt hours to equal the energy in an MCF of gas. For small systems, which is what most of you all have, you pay for systems less than 7.5 horsepower, you pay about 12 cents a kilowatt hour, so that's 58.2, and it gives you about $7. So you can heave a sigh of relief, you're pumping as cheaply as the natural gas farmers are. For large systems, there's a penalty for pumping during the afternoons, so this is an average of about 13 cents, so it costs them a little more, about $7.57 compared to the $7 for a small farmer. All systems, both electrical systems, you have to add $240 a year for site charges. Okay, now we want to talk about sizing the units, and we sort of get away from electrical. I'll mention them as we go along, but this was really geared for engine. Talk was really geared to engines. So we'll have to determine the pump speed and power required, and the northern pump speed, the normal pump speed will be 1750 or 3500, as Dr. Samani pointed out, and we'll have to use the power point curves. For IC engines, you need to determine what gearhead ratio you need, and all units have to be larger than required. For electric motors, you just go one step up if it's a reasonable step. You don't want to go too far on electrical motors, have them way underloaded, because that begins to screw up the power factor. The amperage and the voltage get out of phase, and El Paso Electric doesn't like that. They'll charge a penalty if they catch you doing it. So you don't want to be too big, but you want to be a little bigger. For IC engines, you want to be about 15 to 20% higher capacity than you're going to use, because the engine's going to wear and lose capacity over time. So you want it to have some reasonable life. Dr. Samani pointed out that you'd usually go to this pump curve and be somewhere here on the right. I just picked a point because I'm just doing an example here. This is a pump curve for a pump that's turning 1,750 RPM, and we've decided that that when we match this curve to the pump, that it's going to be operating right here. And he would have wanted me to be down there, but we're here. What we're trying to get is the pumping head, and in this case we have 68 feet of pumping head, and then we project down here to the power curve, and we find that we need 54 horsepower. And notice that this pump comes in 3 different sizes of impellers. That's these 3 curves, but we have to go to the same curve here that we were on up there. So using those figures, we can come in and start sizing our pump requirement. Now, our horsepower calculation, we have a pump requirement of 54 horsepower. You have to put some power into the shaft that goes down through the well, and that's a function of the diameter of the shaft and the length of the shaft. And there's a formula in the engineering section of any pump catalog. That turns out to be about 1.1 for the one I've selected. The thrust bearing has to carry the weight of the shaft, the weight of the impellers, and the thrust of the water coming up out of the pump. So all of that combines to give you a thrust bearing load that says, according to their formula, that you're going to have about 3 horsepower just to run the thrust bearing. So this is the total that you'd get for an electric drive. For an electric drive, you require 58.1 horsepower. You're going to go at least to a 60, and as an engineer, I want a little cushion. I'd probably go to a 75 horse. That'd be about the next one up. For IC engines, we do have a little gearhead loss, part of a horsepower, and so the total for IC engines is about 58.7. Now we're going to oversize it 16% for wear, so that's an 8.5 horsepower. We're going to use a test curve, and the test curve is going to be run under standard atmospheric conditions, which is sea level. So we have to do an altitude adjustment, and a 67 horsepower engine at our altitude will require an engine that will produce about 78 or 79 horsepower, because the altitude decreases the density in the air, and you can't get the power out of it without that air. We got to choose what kind of engines. There's industrial engines, and all the tractor companies provide industrial engines on special order. So it's a self-contained unit, fuel and power connections only. That's all you have to hook up. The disadvantage is it's expensive, and these all come with a radiator and a fan. And with a fan, you're just throwing away 2 or 3 horsepower on the fan. So we want an irrigation engine that doesn't require a fan. Automotive engines adapted for pumping, and those can be engines that the local machine shops have built up for you, and they can all set them on a stand. Or we can go and buy a new one. There's no wasted power on a radiator fan. Requires a cooling coil and pumped water stream. It's got safeties on the oil pressure and the water temperature, but does not have a safety on speed. So on the old engine, I kept that in because of the old engines where you control the speed by just moving the throttle. If you do that and lock it down, if remotely, I assure you, the power shaft were to break when you weren't there, the engine would destroy itself, because without a load, it'll run away. Now the new engines are not that way. They do come with a governor, so they'll control their speed. They're relatively inexpensive. And where do you go for an engine? In the Southwest, you go to Buck's engines. And this is some literature from Buck's engines in Lubbock, Texas. They have 3 sizes of General Motors engines that they use. There's a small 4-cylinder. Their medium-sized one is a V6, 4.3 liter. If you talk cubic inches rather than liters, just remember the number 61. There's 61 cc's in a 61 cubic inches in a liter of displacement. So, and this is one that will fit that will meet our specs. The second one that will meet our specs is a 262. The first one that meets our specs is a 262 cubic inch. Let me back up one. Oops, sorry, I put my finger on the button. This is a V6, and the V6 will meet our specifications in its upper speed range. We said we wanted about 78 or 79 horsepower. We're going to use the little green curve. That's the one for sustained power over a period of time. So that's the one we want to use. And at 8, there's 80, 78 would be right in here. I picked out that it would have to run about 2,400 RPM. It also shows propane. It would let you load it up a little more. Intermittent natural gas, you could go a little higher. But we're going to be running continuously, so we'd be running about 2,400 RPM on this engine. If we go to the next engine up, it's a 5.7 liter 8-cylinder engine, V8 engine, 350 cubic inches. If we look for 80 here, we come to it right there, and the light green line again is going to give us about 1,800 RPM. So, if we took the 4.3 liter V6 at 2,400 RPM, we've got to slow that down to get a pump speed of 1,700, so we'd have to have a 4-to-3 gearhead. The list price for that engine is about $7,000. We could also use the 5.7 liter engine, which gives us our power at 1,700 RPM. It'll let us use an old 1-to-1 gearhead. And there in the valley, you'll find more 1-to-1s than anything else. And that has a list price of about $7,600. The life of this engine is going to be greater than the life of this engine just because of the lower RPM. But you may have to take the gearhead to a machine shop and have a new set of gears put in.
Would the fuel consumption be?
Fuel consumption would be relative to the same.
Relatively the same.
The older engines, if you have one built up, it's liable to be the old compression ratio, which is about 8-to-1 for gasoline. When you have it built up, if you can get them, you want to put in propane pistons, so you go to high compression. These are high compression. Now, whether they come from the factory with high compression or they change the pistons, they're about 9.6 compression ratio. So they're in that hit. But let's see how we're doing on time. Oh, we're in good shape. Now, after you get the engine, there's a matter of making sure it's adjusted correctly. And when you negotiate the engine with the salesman, find out if they've set the engine up on a test frame and tuned it for spark timing and for fuel-air ratio. Now, this is a plot that we did on an old Chevy 292 engine, and we ran it at various speeds. We ran it at one speed and found the maximum power we could sustain with spark advances from 30, 35, and 40 degrees. And then across the bottom we ran air ratios from about 17 or 18 to 1, which is about as rich as it'll run. If you were running a gasoline engine over here, you'd be getting billows of black smoke coming out of it. We didn't do that with natural gas. And then we ran lean ratios up to about 27, 28 to 1. And you notice there's a point missing here. That's because it wouldn't run at that low a lean ratio. And this is like a three-dimensional plot of efficiency with elevation. With maximum kilowatts. So this shows that the maximum power occurred right in this area. And if you project down here, we were also measuring O2 in the exhaust. And we didn't get any exhaust O2 from the rich mixture until we got to a mixture of about 18.5 pounds of air per pound of fuel. And that's where we began to see some oxygen. So we'd call this the stoichiometric ratio. It's when the fuel and the air were exactly balanced, and that's the point at which you get maximum power. 51 kilowatts, which is about 40 horsepower, something like that. And the power decreased then as you went across. So using this, you can set the spark advance up here between 35 and 40. And several of the farmers' engines that we checked, we had to get the farmer to come start the engine because he had to retard the spark in order to get it to start. And then he'd bring the spark up after he got it started. So he was operating way up in this high range. I don't recommend it because you don't want the engine to fire backwards. It doesn't like to do that. But this gives you a point you can find. If you get the engine running under load, you go out there with a pair of gloves and get on that ratio, on that thumb screw that regulates fuel-air ratio. And if you screw it down, you're making it lean. You're going over that way, you're going to drop off. And so you back up. And if you get too far over here on the rich side, if I can find the button again, you're going to drop off power. This is going to be the maximum power that you can get right in this rich zone. Now, you should be able to find that. That'll be the point at which the engine is pulling the greatest load. It has its greatest capacity. Now this is efficiency. And you see that efficiency peaks out right over in here where you've got a little excess oxygen. That's because you're getting more complete combustion at that point, and we're getting efficiencies up in the 22 and 23%. Normally, when we go to test a pump on a farm, we'd find 20 or a few less. Very few of them were at this high efficiency. The best efficiency we ever found on a pump was 26%, and that was an old Minneapolis Moline running with a beautiful load on it and fully loaded. And so it was getting that kind of efficiency. Now, so when you come here and you find this point, then you want to lean it down a little bit because you want to really be running in this point. That's where you're going to get the most efficiency. So tune it to the highest speed and then back it off a little bit on the fuel-air ratio. This is just a chart that kind of shows you the effect of a compression ratio. This is an old 292 compared to a 250 with an 8-to-1 compression and 9-to-1 compression. And at the maximum power is aided, the higher compression will, even though it's a smaller engine, will produce more power and more efficiency. And at 40 degrees, more power, some reason got about the same efficiency. But there's always an advantage if you're having them, if you can get them in an overhauled engine, you're going to want to put in propane pistons. So the conclusion from this is that natural gas, of course, the most economical fuel. Electricity is about equal. New NC engines must be matched to the load and loaded to about 85 or 90% of capacity at our altitude. SI engines should be tuned for maximum engine, lean air fuel ratio, early spark timing, and keep the engine in reasonable condition. At the end of the season, you ought to go out there and pop off the valve, pop out the plugs, and pull the throttle wide open and run a compression test on it just to see what kind of shape you're in. If you find a low cylinder or two, squirt some oil in them and run a wet test. That'll seal the rings. So then you know if you still get the low reading, you know you got a valve problem. And it gives you a chance to work on that valve problem before it ruins the head or something. And lastly, be prepared for higher fuel prices. We may be the leading country in the world, but other people are beginning to compete for hydrocarbon fuels. So diesel fuel and propane are going to continue to go up. Natural gas in the United States appears to be very stable. Whether it will continue that way as people begin to shift on to natural gas. And another thing that's staring us in the face, atmospheric carbon dioxide is going to become a problem, and we're not doing anything to limit our production of it. So someday we're going to have to do some remediation. Money's got to come from somewhere, probably from the users of carbon-based fuels. One of the things I didn't mention, and a fuel for the future, is hydrogen. You can make hydrogen with solar and water. When you consume the hydrogen, you put it in a fuel cell and you break it into And you recombine that hydrogen back with oxygen, you make water. No contamination. But it's hell to store, it's hell to make. And we haven't worked out the wrinkles yet. So those of you who are young enough to work on something, boy, we could sure use some work in that area. It's not practical at this point, but maybe in the future. With that, Samani.
Any question?
Question?
Yeah, Tom, question.
Dr. Abernathy, is there a rule of thumb for engine life in terms of millions of RPM? Is there something you use?
I don't have a number for that. It's just, a car now will run about 200,000 miles. When I was a kid, if you had 100,000 miles on a product, you just put it in the junkyard or overhauled the engine. So they've at least doubled the life of the internal combustion engine. They do that by induction hardening of the cylinder walls, and they've done better on piston rings and pistons. And so the automotive industry has come a long ways. But you can kind of think, how many revolutions would I turn an engine to run, say, 200,000 miles at 70 miles an hour or something?
Okay.
It's a lot.
Do you have a list of well-design engineers?
Of well-designed engineers,
Seriously?
Stuart Mearshite's retired, sorry. He was the last engineer.
Wellpumps@gmail.com. We have some people in there.
We've got a well driller. I'm not in the business right now of working with them, and Hargrave is the only one I've really worked with over the years.
But either through PSL or anybody here at the university, can you get an engineer to come in and just design the well based on?
I can help you if you want.
He-
Yeah,
he-
I'm calling people.
Thank you.
Thank you. Very good.
The preceding was a production of New Mexico State University. The views and opinions in this program are those of the author and do not necessarily represent the views and opinions of the NMSU Board of Regents.